Hi everyone, we are back and we are going to do our pset3 solution videos. So let's go ahead and get started. So pset3, look at the image below and identifying the defects, state the defects and dimensionality defects. Some defects may or may not exist. Vacancies are 0D, so are self-interstitial, so are impurities, so are substitutional. Edge is a 1D defect. Grain boundary is a 2D defect. Void is a 3D defect. Frenkel and Schottky defect pairs are 0D defects. These are not going to exist because we don't see necessarily kind of that ionic crystal where we kind of see those defects form, although you can argue that they actually kind of form in this crystal as well. But again, we don't need to get into the semantics. Vacancy, self-interstitial, impurity interstitial, substitutional impurity atom. Additionally, we see here, this is our edge dislocation. It's that extra half plane that doesn't propagate. And that is it for that picture. All right. Ouch, I just pinched myself. Not in a good way. Anyways, let me quit this kernel and as we read this problem. So the enthalpy of formation for a mystery material, so del HF, is equal to 0.37. And we're told we need to calculate the equilibrium concentration of vacancies at 90 degrees C, 170, 570, 900. So concentration of vacancies equals, if we're looking for a mystery metal, minus del HF divided by, and then I'm actually going to do, we need to be careful. K needs to be 8.617 times 10 to the minus 5. Because that, I believe, are the units for... Let's do Boltzmann constant. Boltzmann's constant, but specifically Boltzmann's constant for the EV. Boltzmann's constant. Let's go back. Boltzmann's constant. Boltzmann's constant. EV units. 8.617 times 10 to the minus 5. Yep, there we go. So let's go ahead and go back. Minus K times T, and XV slash dot T goes to, what do we look at first? 90 plus 273, because it needs to be in Kelvin. So that's my concentration at 90. What about at 170? What about here? And again, you see that exponential increase. 570, and it's quite a bit. And then finally, 900. And you can see that increase each time. How would the value change if we calculate the equilibrium concentration of self-interstitials? The self-interstitials, my delta HF for interstitials, will be greater than the delta HF for vacancies. So we'd have fewer at every single temperature. All right, write the Frenkel and Schottky defects for TA207. Okay, here we go. So let's go ahead. So if we're going to do null goes to vacancy in TA plus vacancy in oxygen. A vacancy in oxygen will give us from 2 minus to 0, so that's a plus 2. So then tantalum is going to be plus 7. So it's going to be plus 7 to 0 is going to be minus 1, 2, 3, 4, 5, 6, 7. So we need 2 of these. We need 7 of those. If I do TA X goes to vacancy of TA 1, 2, 3, 4, 5, 6, 7 plus TA on the interstitial site 1, 2, 3, 4, 5, 6, 7. And if we do oxygen here, we do vacancy of oxygen plus oxygen interstitial 1, 2. And there we go. So we've got all of these. Which one will be dominant? The lowest activation energy. So that's going to be the Frenkel anion, which is going to be this one. All of these are intrinsic reactions. All right. So for any extrinsic reaction, what can exist on site X and Y in our KV notation? So for an extrinsic reaction, for example, I have my impurity going into my host, and then I have a reaction. So on my X site, what can I have? I can have a vacancy, and specifically it's a vacancy of my impurity. Or actually, excuse me. well, vacancy is what's on the site right now, excuse me. I could also have atoms that are from the impurity. Y, I can have an interstitial, or I can have atoms that are on my host. So atoms from the host. So that's basically kind of going in there. Excellent. So let's get into some reaction writing. Let's delete this. Let's zoom in here. So we need to incorporate CaCl2 into NCl5, CaCl2 into NCl5, CaCl2 into NCl5. So one needs to be an anion interstitial. So I need to have a Cl on an interstitial site. I need to have a cation interstitial, so Ca on an interstitial site. And then one has to have a substitutional cation, which is Ca where N must be. So interstitial Cl, that's a -1. So let's go ahead, and I'm going to go ahead and do -1 plus, I'm going to put, for example, a Ca where an N should be. So that's 5 to 2, so that's going to be a -1, 2, 3, plus vacancy of, I need a positives now, so I need vacancies of Cl, which is just going to be -1 to 0, so that's going to be +1 here. So I need 4 of those to be charge balanced. So CaCl, and then what I need plus 2Cl, ClX. So Ca, actually I only need 1, excuse me. So let's do, okay, so right now I'm charge balance with this, so we're good. Ca, Cl, Cl, so I'm good there. N, and 5Cl, got it. So interstitial this, 2 plus, now I need to have a, actually we'll do this right here, Can, so that's going to be a 1, 2, 3. So I need a 3 here, I need a 2 here. Good. So that's a 3, so I need plus 6. Uh-oh. Actually, yeah, 6. All right, maybe this will not work. Because here's the problem, Cl, Cl, X. So then I'd have 3Ca. Ooh, actually, that's why I need 5Ca. There we go. 5, because I have 5Ca, so now I need 10 of those. Now this makes sense. 10. So N, I have 2 of them. Cl, got it. Fantastic. We all already know that this is going to be a -3. I'm going to go a little bit simpler, so I'm just going to do plus vacancy of Cl, which is going to be here. I'm going to put a 3. So Ca, and then I just need to do plus 2Cl, Cl. So CaCl2, good. N, there's one of them here. I've got 5 Cls. Got it. Done. Fantastic. All right, let's go to the next. I should have just, I don't know why I'm erasing. Just want to switch it up. Ti3O6 into Ta2O6. So, and then let's just go ahead, an anion vacancy. So vacancy in oxygen. I should put the charge there. Ti3O6. Let's go ahead. Ti3O6 into Ta2O6. And then we need a cation interstitial. So I'm going to do a Ti interstitial, which we'll go ahead and do the charges now. So oxygen is going to be -12, so Ti needs to be +4. So it needs to be 1, 2, 3, 4. And then we're going to have a substitutional cation, so Ti3O6, Ta2O6, T2O6. So then I need a Ti, where a Ta should be. Ta is going to be, So that's going to be a +6 to a +4, so that's going to be a -2. All right, let's get at it. So speaking of which, I'm going to use that to TI where a TA should be. So that is going to give me a -2. And I can put a 3 here and put a 3 here because that will still give me 3 TI. Then I just need to do a plus. I need to do a +6. Ooh, actually, that's going to give me a little bit of an issue. So, actually, sorry, I'm going to do vacancy of oxygen. Vacancy of oxygen +2 plus TI. Actually, excuse me. Excuse me. Plus TI TA -2. So I could do a couple of things here. Because the problem is if I do 2, I need to get these mass balances correct. So I'm actually going to do 6. So 6 TIs, so that's going to be 2. So I need +12 oxygen, oxygen X. So now my balance on the bottom here, so I have actually 3. So I need 6 and 18, 12, good to go. All right, +4, so now I'm going to do a vacancy of TA. TA is going to be, it's a +6. So it's going to be a -1, 2, 3, 4, 5, 6. So I'm going to do a 6 here. I'm going to do a 4 here. Again, I'm going to put a 2 there. Plus, I'm going to do 12 oxygen, oxygen X. What about tantalum? Tantalum, I need to do 2. Interstitial doesn't count. 4 tantalum. 12 oxygens. Got it. And then finally, plus, I'm going to do, how about we do a, how can we, let's do a vacancy of oxygen, which is going to give us, actually, we don't want to do the same one as we did previously. So let's get a little into it. Let's get a little bit imaginative. I'm going to do plus, I'm going to do plus a TI interstitial. TI, and that's going to give me a +1, 2, 3, 4. And I'm going to give me a 2 here. And then that's going to give me 3. And then I need to do +6 oxygen, oxygen X. And so now I've got TA2, 6 oxygens, got it. So we're good to go. Finally, we're going to do Berger's vectors. So I see a defect here. I'm going to pick my tangent vector, which is going to come out of the board here. So that's my tangent. I'm going to pick my starting point here. 1, 2, 3, 1, 2, 3, 1, 2, because I'm going around. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Start, finish. So my start to finish vector there, that is going to be perpendicular. So T is perpendicular to Berger's vector. So that is an edge. Excellent. What about here? I'm going to pick my tangent vector going out this way. I'm going to start right here. Whoops. I'm going to start here. And I'm going to go 1, 2, 3, 4. Actually, excuse me. Actually, I could go that direction. But at first, I'm going to go actually like this. So forget about that. Actually, let's erase that right here. So I'm going to go, starting here, I'm going to go 1. Oops. So again, starting in that direction. 1, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Start, finish, start to finish vector. T is perpendicular, or T is parallel to B. That is a right-hand screw. And that's it. We are done for P-Set 3. See you next time for our P-Set 4 solution videos. Bye.